Beneath the surface of the Pacific, a massive accumulation of thermal energy is moving eastward. Soon, it will alter weather systems across the planet. In June 2026, the Sentinel-6 satellite detected the physical shape of this heat. Ocean water expands as it warms, and the satellite measured elevated sea surface heights hundreds of miles wide. Massive swells known as Kelvin waves pushing toward the Americas. Shortly after those measurements, the National Oceanic and Atmospheric Administration, along with the World Meteorological Organization, made it official. A new El Niño event is underway. Forecasts indicate a 63% probability that this cycle will reach very strong status as it peaks during the winter of 2026 into 2027. While that classification triggers emergency protocols worldwide, scientists are beginning to question if the underlying numbers guarantee a return to the historic super El Niño intensity of the past. The 2026 event is a seasonal shift that will likely redefine local weather patterns well into 2027. But as the oceans rapidly heat, the tools we use to measure these events are changing, and we may be misinterpreting the actual danger. The process begins when the trade winds over the western equatorial Pacific weaken. Without that steady breeze pushing water west, a massive reserve of warm water collapses back toward the east, releasing immense heat into the air above. That localized heating makes the air column less stable. It rises, pulling moisture with it, shifting tropical rainfall to the eastern Pacific. This forces high-altitude jet streams off normal paths, dragging global weather systems into new patterns. This map shows where altered jet streams increase rainfall, enhancing precipitation across Central Asia, the southern U.S., and East Africa. The opposing force creates massive zones of suppressed rainfall, pushing systems away from Central America, India, Australia, and Southern Africa. In the wet zones, the sheer volume of concentrated rainfall overloads local infrastructure, leaving entire communities swallowed by sudden flooding. A thermal shift in the Pacific translates into localized extremes on nearly every continent. It is a distant oceanic anomaly that dictates whether a region drowns or dries out. Those weather extremes immediately affect global food security, forcing agricultural markets into rapid adaptation. At a global scale, rice yields tend to fall about 1.0 to 1.5% below trend, while soybean yields, which often benefit from the shifting rains, tend to increase by roughly 1.5 to 2%. But those global averages mask severe regional collapses. During the 1997 and 2015 cycles, maize yields in Zimbabwe fell 40% below trend as the harvest coincided with peak drought.
Prolonged heat stress and evaporated water reserves compound the damage. Subsistence farmers and ranchers relying on predictable rains are forced to abandon water-intensive crops or liquidate their herds. On a commercial scale, agricultural industries mobilize salvage operations, harvesting early or replanting different crops to survive the erratic shifts. Ultimately, the true gauge of an El Niño's severity is not just the weather, but the stability of the entire global food supply chain. Given these high stakes, accurately forecasting the strength of the 2026 event is critical. Yet climatologists are divided on what the data actually means. The standard measurement tool is the Oceanic Niño Index, or ONI. It calculates the strength of an event by comparing current sea surface temperatures against a historical baseline of typical conditions. That system relies on a stable climate, but decades of warming have steadily raised the background temperature of the entire ocean. Because the index measures absolute temperatures, this warmer baseline is now embedded into the calculations. It conflates long-term climate change with the natural, temporary oscillations of El Niño. This creates a distortion. A moderate El Niño riding on top of a highly warmed ocean records an absolute temperature so high it registers on paper as a very strong event. The metrics governments use to trigger emergency protocols are being altered by the changing climate itself. The physical reality of El Niño is driven by relative differences in temperature. When the eastern Pacific is significantly hotter than the rest of the tropics, it destabilizes the air and triggers the atmospheric loop. While the index may be overstating the relative atmospheric power of 2026, the absolute heat added to the planet is real. This chart of global temperature anomalies shows that strong El Niño cycles reliably push the planet into its hottest years on record. During the 2023-2024 cycle, the combination of a natural El Niño and the warmed background state shattered global temperature records. We are entering a phase where cyclical warming events stack on top of an already boiling ocean, pushing weather systems into states we've never measured. The classification of 2026 matters because these cycles, when paired with a warming ocean, increase the odds that regional weather extremes will play out exactly as the history books suggest.